Conway's Game of Life is a set of rules that control growth for an array of possible cells. These rules are simple enough to be emulated in a wide set of games where digital logic is available. Well, it just so happens that digital logic is possible in Transport Tycoon, so today I'll be attempting to recreate the Game of Life using trains! Before I dive headfirst into train madness, I'll have to explain the rules for the Game of Life. We have a grid of cells that are turned either on or off to indicate living cells. For each iteration of the grid, every cell takes account of any cells surrounding it. The total number of these living cells judges that cell's new state in the next iteration of the grid. If a live cell has 2 or 3 neighbors, it will continue living. If a living cell has less than 2 or more than 3 neighbors, it suffers from under or overcrowding and will not live on. If an empty cell has 3 neighbors, it generates a living cell in its place. These simple rules can create all sorts of cool generation, and this one has to be my favorite. Using logic built with living cells, it emulates the Game of Life in the Game of Life. I don't really know where to start, so here's a circuit diagram that I found. It recreates the Game of Life using only 35 logic gates. I won't be copying this design for the final build, but it does make for a good reference. Plus, it should test the feasibility of this idea. But how does all of this work? Digital logic in my train game? It all has to do with signals. You can emulate 1s and 0s using red and green signals. A red signal takes some kind of effort to achieve, so it represents a 1. Green is the default signal state, so it represents a 0. For your viewing pleasure, I've created a mod that makes signals a bit easier to read. Instead of red or green signals, we have black and green pixels. These pixels are also great for making displays, such as this one I made in a previous video. You can pass these green and red signal values through logic gates to perform simple computations. For example, I can pass a green and a red signal through this AND gate, which then returns a green. AND gates require that both inputs are 1s, or red, for it to output a red. With this information, you can create almost any circuit using only rails, signals, and trains. Hey, the circuit's all finished. Let's do some tests and see how well this thing works. As I alter the inputs, the output state appears to be correct, although there is a tiny bit of latency during the calculation of the cell state. Since most of these logic gates require moving trains to function, their calculation is not instant. Well, that does prove the concept, but I'd like to create my own design. Let's do a bit of planning and run through the problem step by step, solving the circuit as we go. This original design is huge and its inputs are all in one spot. Routing a signal from each neighboring cell to one location sounds like rail spaghetti waiting to happen. This can be solved by creating an array of circuits and taking the state of each neighbor from its location in the array. Instead of routing the states of each input to one spot, they can come from any direction. This doesn't make sense yet, but I have a few tricks up my sleeve that I'll reveal later. If we want these cells to actually move, we'll have to send a signal to each cell telling it when to start calculating. Since this signal needs to hit each cell at exactly the same time, I can weave a track through the grid making contact with each cell at exactly one point. This track will be attached to a clock that will send a pulse at regular intervals. When a cell receives this pulse, it will reference the states of its 8 neighbors and spit up an output state. Since these circuits will be arranged in a grid and each represent a cell, I can put a display inside of each circuit showing the current state of the cell. Well, that's simple enough. Let's actually build this thing. I'll start with the clock as it's the most simple component. There's 2 ways to go about building these. The easiest of the 2 is to make a loop and have a train run around it. When the train hits this signal gap, the clock outputs a red signal. This design may be easy to build, but it scales horribly. I'll likely need a very long clock cycle so the circuit has the time to compute each iteration, and the only way to extend this type of clock is to make it larger. It's also basically impossible to measure precise units of time. Getting an exact amount of time between each pulse is entirely based on the amount of trial and error I'm willing to put up with. Instead, I'll use a slightly more complicated design that gives very fine control over clock speed. In this design, the clock employs a station. This train is ordered to visit this station on repeat, and the order is timetabled so the train has to wait a precise amount of time before running the loop again. In this case, the train sends a clock pulse every 2 days, plus whatever time it takes to circle around. I can set any number of days to wait here without having to extend the circle to obscene lengths. Now we can connect the output of this clock to the grid of computation cells. Using combo signals, I can split its output into any number of branches. Each of these branches will then be connected to individual cells in the grid. With the clock figured out, I can start working on the circuit to process the logic for each cell. This is by far the most complicated part of the entire construction and will definitely take some explanation. For the next part to make any sense, I'll have to talk a bit about self-regulating networks, or rather, how trains operate when they have no orders. In this example, I have a train running on a loop with 2 branching paths leading to the same output. The train obviously prefers the shorter path and will take the right branch every time. This is a result of the pathfinding system searching the preceding tracks and sussing out the path with the least resistance. Now, the Pathfinder does have its quirks, but it can be controlled. There are a number of Pathfinder penalties that a train will consider before picking a route. The Pathfinder penalty with the least player resistance is a 2-way path signal placed backwards. Though these signals do allow trains to travel both ways, their placement impacts a train's willingness to take a path from the opposite direction. As I spam the right branch with these backwards signals, the train recalculates its route to the branch with the lesser penalty. This mechanic will be integral in counting the number of neighboring cells. Here's an example that shows how I can use pathfinding in this way. I have a loop with 2 holding bays, the entrances and exits of which I can control using these 2 marked switches. While the entrances are closed, the trains continue circling around the loop. When I open the entrances, the trains see that the paths into the holding bays offer the least penalty, so they shuffle in. Even though the exits are closed, the trains still find that it's the better path to take. Now imagine that instead of being hooked up to these switches, these holding bays are connected to a neighboring cell. If the neighboring cell is active, it can send a pulse to release the exit signal and let that train run free. Then it's just a matter of collecting, counting, and releasing the free trains, and using the count to judge the state of the cell for the next iteration. After the process is done, the trains will pathfind their way back to the holding bays automatically. Here's that same design, but expanded to the 8 holding bays required for grabbing the state of each neighboring cell. The usage of fringe mechanics such as these are major time savers. Let's compare to another game with an amazingly complex logic system, Minecraft. While you can build any logic using only redstone components, there are tons of mechanics exterior to redstone that can accomplish the same tasks in a smaller footprint. Using problem-solving mechanics that are specific to a game makes solutions a lot more interesting than what would otherwise be a carbon copy of a real-life circuit. Referring back to the circuit diagram from the beginning of this video, I'd like to point out that the leftmost 28 logic gates only function as a method to count neighboring cells. Using magical train wizardry, I've just compressed those 28 logic gates into a funny train loop. This reduces complexity, which reduces build time, which reduces player resistance, which increases my sanity. I'm going to bring up player resistance a few more times during this video, and what I mean by player resistance is the amount of effort it takes for me, the player, to build something. When this circuit is complete, I'd like to have a reasonably large display, which means a ton of cells that I'll have to build and populate by hand, manually. As usual, I'm using the CityMania client, which offers a copy and paste function for Rails. This makes the placement of Rails easier, but there are limits to what this function is capable of. There are a maximum number of actions the paste function can handle that I am unable to find in the codebase and thus am unable to change. I don't know the exact amount, but I do know it's a hair's breadth above 0. Well, when pasting just Rails, it's not so bad, but when you introduce signals, the amount you're able to copy and paste decreases drastically. As I build these components, I need to keep in mind that they need to be pastable, cleanly, and in large quantities. Even under those restrictions, Rails are the least of my concern. The thing I'm most worried about is populating each cell with the trains needed to perform logic. Here's a working example of what I mean. These 3 logic gates are the backbone of this whole operation. Let's see how each of them fare against the player resistance test. AND gates require no trains, only rails and signals. There is nothing I have to do to get this thing running properly, except for pasting said rails and signals. NOT gates require 2 trains, but this design allows for a quick purchase of those trains, and 1 click to set them loose. This requires 6 clicks and a key press, already 7 times the work of an AND gate. OR gates are my worst enemy. They require only 1 train, but after I release it, I also have to destroy the train depot. 6 clicks, 3 key presses, and I have to time the deletion of the depot. It may not seem like that much extra work, but with a large display, there will be a lot of trains to place. Any extra action beyond placing rails provides a failure point during construction of the final circuit. Vanilla Transport Tycoon also has a hard cap of 5,000 trains, so I do have to stay within that budget. Anyways, back to the circuit. Here's a mock-up of the neighboring cell detector. I've got a dummy signal representing the state of the neighboring cell and a clock pulsing every few days. When the neighboring cell is active, the clock pulse sets the train free and it takes a lap around the circuit. This also functions as the border of the cell, and as you can see, it's diagonal. I need to bridge the gaps between the cells using, you guessed it, bridges. Unfortunately, bridges in Transport Tycoon only build in straight lines and can't be built diagonally. Topographically, the only way for a cell to hit all 8 neighbors with straight bridges is to have the cells oriented on a diagonal grid. This is just one more step on my journey to train madness. Lucky for us, diagonal, in the sense of Transport Tycoon, is actually head-on with the viewing angle, so I guess it's sort of a win. Sort of. Let's take it one step further and design a full cell with all 8 neighboring cell detectors. Well, this thing is huge, and I actually did have to employ some logic gates after all. The incoming signal from each neighboring cell had to be inverted to play nice with the logic controlling the holding bays. Even without the cell state logic, this thing already requires that I place 24 trains per cell. You may also notice that the free space required for a display is rapidly shrinking. I decide at this point to outsource the display to a grid far removed from this, connecting them at distance using tunnels. This should end up being the best of both worlds. The logic can be absolute madness and the display can be clean and seamless. Introducing the circuit components Mark 1. Since the cell grid is a repeating structure, pretty much everything can be boiled down to a handful of simple components. The intercell grid is composed entirely of edges and junctions. A cell is composed of 4 edges, each of which have 2 neighboring cell detectors. These edges are merged together using a junction component to form a square. Since these components are completely modular, I can build out whatever size screen I'd like. All that's left now is to fill the empty space within each square with the logic deciding the state of the cell. This part took a really long time to figure out. This is what train madness really looks like. There's no way to explain what's going on here. Well, I guess it's a good thing that this prototype didn't work. The cell state logic took several attempts before I landed on a design that functioned properly. Counting the trains and dictating the cell state was easy enough, as I can reference the original circuit and place the handful of gates required for that functionality. Saving and then referencing the previous cell state was a different story though. This problem stumped me for at least a week. I couldn't brute force it using simple logic gates, and if I could, I have no idea how. Running into a wall in a situation like this was pretty brutal, and there's not exactly reams of documentation about this stuff. Lucky for me, I know of one singular person who makes Transport Tycoon content who also focuses entirely on train logic. GeoGRFs is, to my knowledge, the best out there at making trains think, and in this video demonstrates a toggleable memory cell. This is exactly what I needed. When I advance the train around this loop, it saves the incoming signal state from the left into this memory cell in the center. After the state is set, it can be read from the other side of the cell. There's only one final piece to this logic puzzle. The neighbor detecting trains need to drive their way to the counting bays to be tallied for calculation. The distances they travel vary widely based on which neighbor they represent, and any number of the 8 total trains may be taking this route at any given time. I have to wait until all trains are present in the counting bays for the logic to be performed and for the cell's new state to be saved into the memory cell. To solve this, I can use another smaller clock inside each of the cells. Stations don't behave well when copy and pasting, so I'll have to employ a wicked long track loop that lasts the bulk of the duration of the iterating clock cycle. Let's welcome back our good friend, the Kirby Ball. Yes, the slowest train in Transport Tycoon has a very big job here. Its snail-like speed allows me to cut down on the size of this loop drastically. While this is a clock, it will operate differently than the one I showed earlier. This functions more as a timeline, activating different parts of the circuit as it progresses. The first segment opens the counting bays so the trains can pathfind their way in. This also closes the exit of the counting bays so the trains don't wander off before being counted. This segment lasts long enough so that any number of trains have enough time to get here. When the next segment is activated, the state computation has finished and the output is saved to memory. It's a bit harder to show, but it is working as intended. The final segment releases the trains from the counting bays and sends them back to the neighbor detecting bays. When all is finished, the new cell state is waiting in memory to be shown in the display and to be used in the next cell iteration. The cell state logic comes in way over budget in terms of being pastable in one go, but it's no big deal. Splitting the circuit into layers to be pasted individually solves this issue pretty well. All of the necessary components are finally complete. Let's put this thing together and do a test with a small grid of cells. This is a good example of why I designed these components in the way that I did. Everything lines up perfectly with very little thought required on my end. The rail portion of this construction doesn't take very long at all, but spawning the trains in is a nightmare. This design requires 42 trains per cell, a lot fewer than I was expecting, but still enough to cause me anguish. 9 cells in total requires me to spawn 378 trains, one by one, in specific locations and with no margin for error. The actual final build will be way larger than this, and I am very much not looking forward to building it. Might I say that this contraption is looking very cool. It's finally time to test it. Let's see what happens when I set all the cells to be active, and to make things a little easier to follow, I'll put the correct output in the bottom left. Alright, nothing is happening. As it turns out, bug fixing an army of renegade trains is a bit harder than one might expect. When the clock is too brief, the trains get stuck. If I've misplaced even one signal, the trains get stuck. In this case, I wired the wrong signal to the memory cell. I figured that inverting the output would make the display a little easier to read, but it ended up polluting the data that other cells were reading. Alright, let's try it again. It actually works. This pattern is known as a blinker. It's a line 3 pixels in length that changes its orientation every iteration. Do keep in mind that the display states are now inverted. When I actually build the display, it will output in the correct manner. Just think of this as some kind of programmer art for now. I know there's very little stakes as a viewer, but you should know that by this point in the build process, I was about 3 weeks deep into train madness. Seeing this circuit come to fruition was a huge weight off my shoulders. There's a few bugs left to fix, but the concept is fully proven and operational. Well, time to scale it up. But just how big will this grid be? Vanilla Transport Tycoon allows a maximum of 5,000 trains, and each cell requires 42 to be functional. This means I can build a maximum of 119 cells. Just to be safe, I'll aim a little lower and build a 12x8 grid with 96. Let's go building! I'll likely get some comments about this, but I am aware that the JGR patch for Transport Tycoon includes programmable signals that make all of this nonsense trivial. Honestly, I would have preferred using JGR for this, but that version doesn't support the copy and pasting of rails. And looking back now, maybe it was cooler to use pure train logic. If I was using programmable signals, I'm really just programming, and I could program something like this in an afternoon. Hey, it's all done. I'm not really sure what to say here. This thing is massive and completely packed with rails. Over 200,000 to be precise. I still have to connect the output of each cell to the display, but this is good for now. I think it's time to add some more trains. You know, I like to add some more trains. Quite a bit, but too much of a good thing is a bad thing. And this was a very bad thing. There's 96 cells with 42 trains each. That's 4,032 trains in total. 4,032 precisely placed trains spawned one by one over a large area requiring tons of panning, removing spare depots, all while making sure that nothing is awry. I spent over 4 hours adding some more trains. I even made a speedrun out of it. Check out this route. Place 2 trains in each of the 8 NOT gates on the edges of the cell, then spawn the 8 neighbor detecting trains in this depot. Then I move to the interior. I already know I'm getting there in the perfect line. 2 quick ones. I spawn all the NOT gates in pairs. Then I move on to the 2 OR gates, my arch nemeses. But I get the 1 cycle and remove both depots before the trains get the chance to run back into them. All that's left is the Kirby Paul and the 2 trains used to start the cell clock. I just have to do that 95 more times and I'm finally finished. I think it's fair to say that you're not going to find train content like this anywhere else. That being said, it's not like any sane person would make this kind of content anyways. For how utterly insane this looks, it's also incredibly laggy. I guess it was lucky to separate the display from the calculation because panning the camera over this monstrosity drops the FPS to about 5. Speaking of the display, it's time to make some pixels. I designed the computation cells to output their states into a row aiming diagonally through the grid. This allows me to pack 8 cells worth of data diagonally and output it into a diagonal row of pixels in the eventual display. It may seem wacky, but remember that bridges and tunnels can only be placed in straight lines. And straight, in the context of the cell grid, is actually diagonal. It's probably obvious that I'm swimming in technical debt at this point, but sadly, it's all by design. All I have to do is design a pixel component to connect with a cell and relay its state into a large grid of signals. I went through a ton of signal layouts, some were more dense and some were less. I kept running into the same copy and paste limitations I had with the circuit components, so some compromises have to be made. Some leeway can be gained by removing most of the signals, leaving only enough for me to extend them after placing. This unpacking of components is something I find quite useful when copy and pasting. It does add some extra build time, but it's kind of worth it in the end. Alright, back to the build. Since the pixels are smaller than the cells, I can greatly compress the output buses from each diagonal row of calculators. And now, with each bus lined up, I can finally build the visual connection to the game of life. When I've got the time-lapse set this fast, it's hard to gauge how much work goes into this. This was about an hour straight of placing rails, then control, clicking, and dragging signals to extend them and unpack the pixels. I think my wrists need to be studied for some form of immunity to carpal tunnel. The display isn't all I'm building here. What would a game be without some kind of user interface? Since the circuit is running completely off screen, some controls over by the display would be very nice. A switch to toggle the clock would be pretty handy. I'll also build a progress bar. The green bar starts shrinking as the cells begin calculating their next iteration. When the bar is empty, the circuit rests and waits for the signal to start the next iteration cycle. Now for the finishing touches. What's a user interface without some kind of label? I christen thee the Train of Life. This is by far the craziest thing I have ever seen in Transport Tycoon. I mean this in a non-deprecating way, but this thing really shouldn't exist. Well, let's do some testing. There's a handful of issues I'm only experiencing now that the construction is finished. The most apparent is the difficulty of manually changing the state of a cell. I never thought to implement something like this during the small-scale tests, but in hindsight, I probably should have. Manually flipping the state of the memory cell isn't that bad, but I wouldn't call it user-friendly. I'll do a stress test with a pattern a little more complex than before. A glider is a very small pattern that moves diagonally through the grid. Hopefully, if any cells do have an issue, they should sweep across the grid and find it. Or maybe you can find an issue immediately. Bug fixing is not usually fun, and I feel that's exemplified here. And it doesn't help that this is what I'm working with. Go ahead, find the bug. This signal on the exit of the counting bay was a little too much for the trains. They were leaving the bays too close together and getting jammed finding their way back to their homes. This error is present in every cell, but I won't force you to watch me fix them all. Alright, let's try it again. Hey, this is looking a lot better. It bugs after 2 iterations, but that's twice as good as last time. I sourced the issue to some stuck trains in a handful of cells. Most of these cells haven't even been active yet, so I can only assume it was caused by some edge case while populating the cells with trains. 3rd time's the charm. That seems to have fixed all the issues for now. If you're wondering, the cells treat any space outside the grid as a dead cell, so when the glider hits the edge, some funky game of life logic happens and it morphs into a square. Squares are a stable shape and will not change unless disturbed. Well, let's try another pattern. This is the lightweight spaceship. It's a bit like the glider, but larger and it moves orthogonally instead. Hey, another successful test. It even morphs into a glider upon collision with the edge of the grid. Now for something that should push the cells to their limits. I went searching for the noisiest pattern that would fit inside the confines of the grid. That ended up being the tumbler. The tumbler is an oscillating pattern that repeats every 14 iterations. And by the way, I'm sourcing these patterns from the Conway's Life wiki. If you're looking for some deep lore to dive into, there's plenty of cool stuff there. I guess this pattern was a little too much. It runs well for a bit, but at some point a cell calculates the wrong output and the oscillator disintegrates. I'd like to think that I'm sick of hunting bugs, but really I'd like to get this contraption running as well as I can. And it turns out that in row 7, column 2, I forgot to delete a singular depot from this OR gate. Very fun. That seems to have fixed the issue. It's wild to know that this is all running using trains, but let's talk about the frame rate of this thing. It does run pretty fast for what it's doing, but it could be running a lot faster. As it stands, the circuit runs at about 25 times simulation speed, assuming you're not looking at the calculation cells. I've got the iteration clock set on 2-minute intervals. Assuming 25x simulation speed, that's around 1 frame per 5 seconds with fast forwarding. The biggest detriment to the frame rate is definitely the speed of the neighbor detecting trains. They have a long path to take and are very much not the fastest train available. You may be wondering why I didn't just build this whole thing using maglevs, the fastest trains available in the base game. Well, through my own testing, I found that the SH40 electric train is the most consistently performing for logic gates, and that's well and good, as logic gates barely take up any of the time in this circuit. The real issue is that different rail types cannot share the same tile diagonally. Since this construction had to be compact, mixing maglev and electric rails wasn't an option, and thus maglevs couldn't be used. There are mods for logic trains that drive on any type of rail, travel impossibly fast, and are purposely built for applications such as these. Alas, my commitment to the vanilla train set is just too strong. Plus, it's fun to know that this monstrous creation is running completely mod-free, except for the signal graphics. But to be fair, a display like this would be impossible otherwise, and it makes the viewing experience actually bearable. Besides all of that, I'm sure some optimizations could have been made to the cell logic. If prototyping wasn't such a hellish experience, I know I could have dropped the train count a considerable amount. Anyways, let's do one last pattern. This one is called Mango with Block on Dock. A large, stable pattern that does absolutely nothing, but it works like a charm. Alright, I can't let this be the last one. How about Octagon 2? Very cool. Well, that was a fun adventure. There's more than likely a few bugs I have yet to find, but I don't think I can handle any more of this. As usual, I'll put a download link to the maps I made in this video, plus some instructions for operating the game. Alright, that's all I've got. I'll see you all soon, with something that doesn't require 4,000 trains.